Alright, today we're going to look at another gas law, which is Avogadro's gas law. We've looked at Boyle's law, we've looked at Charles' law. We're now going to look quickly at Avogadro's law. And the reason I say quickly is because we already know the basics. We already know the general idea of how to deal with gas laws. I'm not going to go through the derivation like I did for Charles and Avogadro's, because all we really need to know is how are the variables related. And you should know in general what Avogadro's law is based on the concept I'm going to tell you. What he did is he looks at number of moles and the volume, keeping temperature and pressure constant. So essentially, if you have a gas in a container, you got this gas kind of in this container, and I put more gas into it, that's what moles are. Moles are the amount of gas that's put in. So I add more gas, right? More gas is added to the container. Well, if I put more particles in, it's going to collide more with the container. It's going to cause the container to expand and get larger, right? You know this anytime you've filled up a bicycle tire with air, or if you filled your car tire with air, you're putting more air into the container, the volume is going to increase. So there's a direct proportionality between the amount of gas that you put in the container and the volume of the container. Okay, that's pretty much Avogadro's law. So what it essentially allows us to do is it allows us to count how many gas molecules are in our substance. And this is what led Avogadro to the concept of the mole. Now, he didn't call it a mole, but he did come up with this idea that gases in a container, as long as they are the same gas at the same, well, not even the same gas, but if they're at the same temperature, pressure, and volume, then they had to have the same number of particles in it, regardless of what kind of gas it was. Okay, now this is something called molar volume. This will be a little more useful when we get into gas stoichiometry, and actually I'm not a big fan of molar volume, but the idea is that if we have 1 mole of gas, which is considered an ideal gas, and I'm going to define that in the next unit when we talk about ideal gases, we'll have a volume equal to 22.4 liters whenever we have 1 mole. Okay, so if we have 1 mole of gas, we're going to have a volume equal to 22.4 liters is what this molar volume means. Real quick, what this means is that if I have pressure, okay, I probably should define what STP is. STP stands for standard temperature, okay, temperature and pressure. That's essentially what it stands for, STP, standard temperature and pressure. Our pressure is going to be set at 1 atmosphere. So by saying STP, and you'll see this a lot in some homework problems, by saying STP, it's a quick way of saying my pressure is 1 atm and my temperature is equal to 0 degrees Celsius, or it's equal to 273 Kelvin. Well, if these conditions are true, and I also have my moles are equal to 1, well then my volume has to be equal to 22.4 liters. Okay, that's essentially what's known as molar volume. What it does is if I have these conditions, every mole is 22.4 liters. So if I had N is equal to 2 moles, well then I know that my volume has to be equal to 44.8 liters. Okay, and like I said, that'll be a little bit more important when we get into gas stoichiometry. So let's get to Avogadro's law, or at least an application of Avogadro's law. Now, we saw this before when we looked at Charles' law and we looked at Boyle's law. We looked at ways of calculating. We're going to use that equation, V1 equals N1 equals V2 over N2. This should look very similar to Charles' law. Remember, with Charles' law, we had V1 over T1 and V2 over T2. If you need to, go back and look at that video, because they were directly proportional, just like Avogadro's law. If they were inversely proportional, it would mimic and imitate Boyle's law, which is multiplication as opposed to division. All right, so what we're going to do here is I'm going to list the information that I have. I have a container that holds a gas. Okay, so I've got this container that holds hydrogen gas. I had hydrogen gas in here, and the mass of the gas that I have in here is equal to 83.45 grams of hydrogen. Okay, well, the volume initially of the container is equal to 185 milliliters. All right, what I'm going to do is I'm going to add more gas to the container. So what I'm going to do here is I'm going to add 2.76 grams of H2. So I'm going to add more hydrogen gas to the container. All right, so my final volume, my volume afterwards, my mass 2, is not 83.45, but it's 83.45 grams plus 2.76. Okay, so my final mass actually comes out to be equal to 86.21. And when that happens, what I want to know is what will my final volume be? Okay, so will my volume get bigger or will it get smaller? Well, you should know this going into the problem, right? If I'm increasing and adding, right, I'm adding this amount of gas to the container, therefore the volume should go up, right, directly proportional. All right, so to do this, we need to keep in mind that we're talking about moles in this problem. So what I'm going to do is I'm going to convert these to moles, and you might want to refresh your memory on how to convert from grams to moles, right? So what I'm going to do is convert these from my initial conditions to my final conditions. I want to have these both in moles. So my mole over here for 1 is going to be equal to 83.45 grams of hydrogen. What I'm going to do is use molar mass to get rid of the grams of hydrogen and convert that to the moles of hydrogen. So that would be equal to 41.32 moles of hydrogen. Okay, so I've got my moles of hydrogen. My final moles of hydrogen that I'm going to have, okay, final moles of hydrogen will be equal to 86.21 grams of hydrogen. Again, 2.02 grams of hydrogen on the bottom for every 1 mole of hydrogen. In this case, when I do this calculation, I end up with 42.68 moles of hydrogen. Okay, so I have my final number of moles, my initial moles, my final moles. Now what I'm going to do is I'm going to use this equation and I'm going to solve for my final volume. And when I do that, I'm going to multiply both sides by the number of moles and bring that over here. So my equation that I'm going to use for this is going to be V2 is equal to V1 N2 over N1. All right, again, just using some basic algebra to bring my variable over here and solving for this variable. I'm going to go ahead and plug in the numbers. Again, here I'm looking at carefully what numbers do I have. I've isolated my volume 1. I'm looking for volume 2. I have my moles of 1 and my moles of 2. Just be careful that you're plugging in the right numbers here. 185 milliliters times my moles of 2, which is 42.68 moles of the hydrogen, over moles of 1, which is the 41.32 moles. Make sure you see the decimal here. And notice that the mole unit cancels, and my final volume comes out to be equal to 191 milliliters, and that's rounded with correct number of significant figures. Okay? All right. So if you want to stop the video, you can stop right now, but I'm going to show you something in here that a little shortcut if you want to just stick around for another minute or two. But that's essentially Avogadro's law. What I want to show you is a little bit of a shortcut kind of thing here, because if I'm using the same gas, if this is hydrogen and I'm ending in hydrogen, as long as I keep the molar mass the same, notice what I did here, divided by 2.02, I divided by 2.02. This problem will work exactly the same way if I do 185 milliliters and I actually keep the mass in here. So if this is confusing to you, it's probably better just to make the conversion to moles and plug in. But take a look at the math. If I'm taking that 83.45, dividing it, and then dividing in the equation, wouldn't these both essentially cancel out? If you understand what I'm talking about, great. If not, you'll be okay with doing this the other way. So I can actually keep the mass in here, and I can keep this mass here. Now, where this will not work is if I change the gas, if I change this from hydrogen to another gas. And typically in Avogadro's law, we don't do that. We don't change it. So I would end up with 191 milliliters as a result as well. Okay, so it's a little shortcut. You can actually skip this whole step for converting to moles. The only time you cannot do that when you have to keep the moles or convert to moles is if you change the types of gas. If I change from hydrogen and I added another gas. We're going to actually do that with Dalton's law, so for right now you should be okay with skipping that. Alright, so thanks a lot guys, and I'll see you later.